So for this problem, let's say that our system is just the box, and we'll represent it with its center of mass. There is some weight component going down, and then two tensions, one up and to the right, the other up and to the left. They both have the exact same angle, which we see is called theta, from the vertical. So when I turn T2 and T1x into, T2 and T1 into T2x and T21, I have to be careful because this angle is actually adjacent to what will become my vertical component and opposite to what will become the horizontal component for each of these tensions. So that means T1x is actually going to be opposite. So that means it'll be the magnitude of tension times sine of theta. And again, that's T1. And T1y will be T1 cosine of theta. Now that's a bit backwards, and it's just because they're using different angles. T2x is going to be the tension in this rope, the second rope, times sine theta, and then T2y is going to be the second tension, magnitude of the tension, times cosine of theta. Okay, so these are our components, and we're going to use these when we add up the forces. And I'm going to go ahead and draw them like this, because it's easier to see. T2x, T2y, T1x, and then T1y. If you wanted to draw them on the other side, remember that this is just the force vector just represents the hypotenuse, and I can move this x component up and this y component over, and it'll still make a triangle with this theta as the inside angle. When I draw the forces like this, though, I can see that the T1x and T2x need to be balanced, or they're going to be in equilibrium. So when I add up all of the x forces, like this, I'm going to get T1x equals T2x, minus T2x, those add up to 0, and so I can say T1x equals T2x. Great, so now this lets me think about T1, sine theta, which is the x component, and how that is equal to T2 sine theta, which is the x component of tension 2. And since theta is the same for both, then this just drops out, and I realize that the tension in the first rope is equal to the tension in the second rope. This information is helpful because I'm going to need this when I start adding up the vertical forces and see what they equal. Now, first I'm going to go ahead and move these component forces over here so that I can have some room to sum up the y forces. So when I sum up the y forces, I'm going to have T1y, T2y, both of those going up. So I'll write that T1y plus T2y. I did plus because they're both positive, minus the weight. And again, let's assume that this entire thing is in equilibrium because I see no reason for it to want to accelerate. So this means the acceleration of the system, even in the y direction, will be 0, and all of these things will add up to 0. Now I can say that T1y plus T2y are going to minus the weight, are going to equal 0. So what I'm going to do with this equation is add the weight to both sides. And when I do that, I'll get T1y plus T2y is equal to the weight. And let's go ahead and insert T2 cosine theta, T1 cosine theta for T1y and T2y. So this becomes T1 cosine theta plus T2 cosine theta is equal to the weight. Now, what's great about the fact that we added up the x forces over here was we found that the tension in the first rope is equal to the tension in the second rope, or the second side. So what I can do with that is just replace either one of these. Or something that I could say is I could just call it T. If it is T1 equals T2, I could just say that they're both T. And T1 equals T, T2 equals T. I don't know how you want to think about it. And when I draw this equation over here, then I can just say that this is T, and this is T, the tension of the rope, And again, if you wanted to call that T1 cosine theta plus T1 cosine theta, you could do that. Or now you could say T2 cosine theta equals T2 cosine theta. Either way, you're going to see that this becomes 2T cosine theta equal to the weight. And when you need to solve for T, the tension, then what you would just do is divide both sides by 2 times cosine theta. And when you do that, you find that tension is just equal to the weight of the object divided by 2 cosine theta, which is option D.